the very top here, we just have to start by telling Python what knowledge we want Python to have about calculations it can do. So we're going to get it to import this NumPy package again. So that's got lots of tools for doing calculations. And then we're going to get it to import VESIcal. So that has all of the information about doing solubility calculations. So we run that. Mine runs very fast because I've already imported them when I checked it was working. Yours will be a bit slower. Shout if it doesn't work. I'm just going to keep going, assuming it does. If enough people say it's not working, we'll stop. Otherwise, we'll try and write in the chat and help you. So we've now told the notebook sort of how to do things, but it doesn't have any knowledge of the samples that we're interested in. And so that's the first thing we need to do, is to give it a sample composition. And so in this cell, we've got a composition of, I think, a melt inclusion or a rock from Kilauea. Maybe Penny will clarify that in a minute.
Yeah, it's a melt inclusion from Kilauea.
Great. And we've just listed out the major elements here. Now, you don't need to understand what's going on in there, apart from, if you have a particular composition you want to run, you just need to know that you can click in the cell and change the numbers, so on. And it will work for your calculation. And then to run it, you do this shift enter thing, or you can go up to the top here and press run. That also works. And we haven't asked it for any output, so it doesn't tell us anything. We know it's run because it didn't produce any scary red boxes with errors in. It has this number appear here. And then we want to actually do some calculations with this composition. And I should say we've tried to make it so that VESIcal will always work in the same units the whole time for everything. So VESIcal only knows about weight percents, and that includes for water and CO2. So this cell here, we can do our first calculation. And I've tried to add these labels to explain what's going on. And what this calculation is going to do is say, well, we've got this magma, and let's assume we're going to put this magma at a pressure of 1 kilobar or 1,000 bars at 1200 degrees C. And I'm going to record that information in these variables here that I've named P and T. And then we also need to say, well, this melt is seeing or is saturated in equilibrium with a vapor, with a water CO2 vapor, and that vapor has is exactly half water and half CO2 in terms of mole fractions. So the same number of molecules of each. And again, putting that into this variable here. And so now we get to the line where we tell VESIcal what calculation you want to do. And so when I imported VESIcal, I told it to name it V, so we can access all of its knowledge just by writing V in the cell. But again, I'm explaining this, but you don't need to know this or care about this. You just need to know how to change things to suit what you want. So I've got V, and then I'm telling it to use this particular calculation type. So calculate dissolved volatiles with underscores in between. And then we have to give it the information about the calculation. So sample is Kilauea sample. So again, we stored that as a variable up here. I'm giving it the pressure and the temperature and the fluid composition. And that runs the calculation and stores it all as this, what we call a calculation object, which we put here called calc, and then we can view the result with this line just here. So if I run that, it will take a little while, and it will spit out the results in terms of how much CO2 and how much water is dissolved in that melt at those conditions. Now you might be thinking, well, Penny talked about a load of different models during her talk. Which model is this using? Well, we didn't specify anything. And so when you don't specify what to use, it will use MagmaSat. But there's other models built in. We can compare the results using these different models. But maybe I can't remember what Penny talked about, especially after that long interlude of trying to get the computer to work. But we have a way of finding this information. So we can get all the model names using this command just here. Or you could go to the documentation for VESIcal or the papers. You can see it like that too. And we have this big long list of models. So now we can do this. We can run this calculation. And so I've got a very similar cell here again. We've got calculate dissolved volatiles. I'm giving it all the information. And this time we've got this additional line here. And we're using the Iacono-Marziano model. Just indicated that there. So again, what you could have done to get that cell is just gone up here, highlighted all of this, copied it, and then pasted it down here and just gone in and added or edited this line, and you could ignore the rest of it and what's going on. And then can run that calculation. And now we get to some science. We've now got two results. Do they agree? Well, hopefully they do. So we've got 2.87 weight% of water dissolved according to the Iacono-Marziano model. Oh dear, this is quite different from what MagmaSat predicted. And what about CO2? Well, we've got 0.05 weight% there. Well, it's maybe a little bit closer, but I'm not sure I would say that was close. So Penny's going to talk more about that science point in a minute.
Should we just get people to run Dixon quickly to make their own cell and then type in the chat what result they get?
Down here, there's an empty cell, or add your own. And you can do the same thing. You can copy this code or paste it there. Or you can just go into this cell and put in a model name that you want to do and just see what comes up with if you use the Dixon model, for example.
And then in the chat, if you could type like CO2, like the model name, say like Lou, and then CO2 and what you get, so that we can just see all the different numbers popping up depending on what model you've played with. If you use a model outside its calibration range, it is, do you want to try Lou, Simon, and see if it kicks up an error just to show that? It should do this.
Sorry, I got lost in the notebook.
Are there any modules that can quickly check the calibration range? No, the problem is I couldn't actually compile all the data sets. So like Paolo Papale would not send it to me in a useful form. The MagmaSat one is currently fragmented because everything's moving over to EarthChem very slowly in the pandemic. What we do provide is the calibration data sets for the ones we do have, so you can read those in and make your own cross plots. And we provide a task diagram at the moment in the VESIcal part 2 for MagmaSat and Papale, because that's what we have at the moment, information wise.
And Penny's created some notebooks where you can go in and put your own spreadsheet in there and then compare it directly with the data.
So here there's a warning that's popped up, basically saying like, take extreme care when you're extrapolating Lou outside of haplogranites and rhyolites, because you've just applied a rhyolitic model to a basalt here.
And there's another question. His question is total Python novice question. Is the way VESIcal works fairly standard Python, or there are lots of bespoke methods, object types? For example, calc.result, is that something that would be meaningful in vanilla Python? Wondering if this is a good gateway to learning Python, or if I need to go off and follow some tutorials first. The answer is yes and no. So it's, when we were creating it, we tried to use sort of fairly standard ways that people use to create Python modules, but it's not. So hopefully once you learn one module, it's not a totally different syntax and way of interacting with it, but it isn't in vanilla Python.
But it is a great way to learn Python. I couldn't code in Python before I started working with VESIcal, and now I do absolutely everything in Python. So you will learn things because you're copying and pasting cells, and then you want to make your own thing or your own plot. So yeah, absolutely. I think the best way to learn Python is to have a project like this rather than just sit down and watch a load of tutorials. You said you only get one result. If you choose a model which is just pure water or pure carbon, like Allison carbon Stromboli, it's only going to give you CO2 because it's not like dealing with water.
So we've done the sort of forward calculation, but most of the time we know what the CO2 and H2O, or we think we know what the CO2 and H2O is in the inclusion. And so we can now tell VESIcal what that is. So I've added H2O and CO2 down here. I've just seen a question from, I think it's a great question, so I'm going to answer it. So using the pure models, does it just ignore fluid composition? And the answer is, I am 99% sure. I would need to go to the documentation, which I'll show you how to do a little bit later, but it will not ignore the fluid composition, because what you're really saying is you've got some fluid phase and only 50% of that is water. And so that means the partial pressure of water is lower than it would be for a pure fluid. So if you were to change the fluid composition, hopefully the answer will change. Okay, sorry for that diversion. So we're setting up the sample again. This time we're adding water and CO2, defining the temperature. I run that. And now in a very similar way, but this time, as before, we tell the VESIcal what the calculation type should be. So this time it's calculate saturation pressure and can give us the result. And this time it only needs the sample and the temperature. And it tells us that that particular set of water and CO2 would be stable, would be dissolved at 930 bars. And then,
sorry, there's just a question. That's actually the CO2 and the water content I measured in that melting fusion. So that isn't the calculation above. That's like the direct SIMS measurements I made, just in case you're interested.
Thanks. So before we got you to manually change the model name and see what happened. Well, there's never a reason to do things manually in Python. Unless you want to, of course. You can do anything you want to in Python. So what I've set up here, I'm not going to run through exactly what this is doing. You can read it or ask me about it later if you want. It's just going to do the same calculation for different models and give you a nice printout of the result. And it takes a bit longer because it has to do multiple calculations. And we get different answers again.
And let's just look at this in a bit more detail. So MagmaSat gives you 930, so 0.9 kilobars, and Dixon gives you 1.3 kilobars. That's reasonably different in terms of percentage error at looking at your Magma storage depths.
In these calculations, what we're doing is calculating saturation pressure. But when we were doing it the reverse way, so calculating the dissolved amount, you had to specify the fluid composition. And so if it's giving us saturation pressures, it must also be able to calculate the fluid composition at the same time. And there's another function here. I'm just going to highlight the name again. And this will do something very similar as the previous step and just iterate through the models and tell us the composition of the fluid. But again, I've got various Python here. You don't need to understand what that Python does to play with the model or to use a Jupyter notebook.